Hello and welcome to our webinar today presented by Dlubal Software. Today we will once again be working in our finite element analysis and design software RFEM. The topic for today's webinar is ACI 318 2014 concrete column and beam design in RFEM. My name is Amy Heilig. I will be the presenter today. I am the CEO of the U.S. office and also a technical support and sales engineer. Our U.S. office is located in Philadelphia, Pennsylvania. My colleague Moritz Bertram will be your moderator, answering any questions you may have. He is a product and customer support engineer located in our Leipzig, Germany office. If that control panel seems to get in your way of the presentation today that popped up when you logged into the GoToMeeting, you can go ahead and hide it with that orange arrow up at the top. We also want to encourage everyone to ask questions during the webinar. We'll do our best to get to all of them, but if by chance we don't, I will certainly send you an email afterwards. You can go ahead and ask those questions within the same dialog box. And with that, we can jump into the presentation. So for those of you who are familiar with how our program and our add-on modules work, we probably are already aware of this. For those of you who don't, our main program is RFEM. And this is essentially where all of the modeling, the loading, any load combinations can be generated according to the various standards. We also have BIM integration included in RFEM, such as with Revit, which is a main topic with concrete design, certainly, Tekla, AutoCAD. And here we can do a full analysis of our model. So anything that has to do with internal forces, stresses, deflections, support reactions, this is all within RFEM itself. Now, when we talk about add-on modules, and today we will be in the add-on modules RF concrete members and RF concrete columns. This is what allows us to do design according to the ACI 318. Here we'll be doing ultimate and serviceability limit state design. We'll also be getting our flexural, shear, and torsional reinforcement from the standard as well. So I will jump into RFEM. I want to first start off with, this is our main program, RFEM. I'm not going to be spending really any time modeling today, just for the sake of time. I would rather spend more time getting into the details of our concrete design according to ACI. We have plenty of other webinars online that go into more details of modeling, so certainly check out our YouTube channel for that. So to begin, when we open up a new model, we get this dialog box that looks something similar to this. We're defining, if we'd like a 3D model, we want to classify our load combinations, have them automatically generated, and we also define our z-axis, our global z-axis. And what's typical in the US and Canada is to, of course, have this z-axis upward. You certainly can work with it downward as well. Now, this is something important for concrete design. When you are working with these global z-axis in the upward direction, you need to click on this orientation of the local axes for our surfaces and our members. The default is to have this as upward, and if we set this as upward for the global z, you want to set this as downward for your local axes. This is important because once we get into the RF concrete modules, if we leave this as upward, our terminology top and bottom for our reinforcement will be opposite of what it's supposed to be. Now, if you forget to do this, it's not a huge deal. You'll obviously notice when you have a lot of reinforcing located on your top but none on your bottom for a beam, for example, then obviously the terminology is wrong. You can always go back into this general data and correct that by quickly changing it to downward. So just something to take note of for concrete design. I went ahead and modeled a very simple structure here. We have our column members, just rectangular elements, same with the beam members here. I have a couple surface elements defined for maybe an elevated slab as well as some walls. I won't be getting into any surface design. Our concrete webinar next month, we'll get into design according to ACI for surfaces. Today we're just focusing on beams and columns. The other thing to notice is that I have some ribs defined down here. And if I double click on ribs and go to my general tab here, our beams and columns are typically defined as beams. This is nothing more than just a normal beam column element. But we also have the option to define a rib. And what's nice about the rib is that if we go into the edit member types here, we can define where to exactly place the orientation of this rib in comparison to the surface that it's related to. So we don't have to manually put in these rigid links to drop it down below the surface. The program will automatically calculate that for us. Now what we can also do is automatically set the effective widths. L/6, L/8, or we can enter in some user-defined option here. So it's nice that the program does have this member type as a rib, which is used quite often for concrete members. So you can see here that I've already defined all of this criteria. And the last thing to notice about these members in particular is that if I take a look at these columns, for instance, I right-click and I go to Edit My Member. Under the Modify Stiffness tab, this is something that needs to be done for concrete members. Typically, the default will look like this, definition type none. And what you want to do when you are doing design according to ACI, you will see the drop down here according to ACI 31814. If you click on this, this should look familiar. We have our component types, columns, walls, beams, and flat plates. Well, then you'll see these multiplication factors for our stiffness to take into account crack cross sections. Anyone who's done concrete design, you're familiar with this. This is the way to take it into account in the program. And then obviously for our beams, for example, we have the exact same setting according to ACI, but I've selected the beams here. Now this multiplication factor will be slightly different than what it is for columns, which is why we give you this other drop-down box to define the element. So remember to do so for your concrete design. This is not done in one of the modules, but it's actually done in RFEM. The other thing to notice is that I went ahead and applied some loads here already. We have our typical dead load, surface load here. I put some line loads at the top members. Same thing for live load. And lastly, I put in a lateral load, wind load. I just applied it as a line load as well to what we can call maybe our first level diaphragm here, as well as our second level to these beams.
So we can also take a look at our different load combinations that were generated. If we go into our load cases and combinations dialog box, we'll see here our different load cases, dead load, live load, wind load. But more importantly, we're interested in these load combinations. Now, the load combinations were generated according to ASCE 7. We have all of our LRFD load equations listed here, only applicable to those load cases that we defined. We also have our ASD load combinations listed here as well. Something to note, it is default in RFEM to run these load combinations as second order analysis, or P delta. So you can individually change these if you'd like to something such as linear analysis or large deformation analysis if you have things such as cables. But for now, we want to keep it as P delta effect so that we are doing our member design according to P delta. We also have the results combination. This is nothing more than an envelope solution. You can see that we have the envelope solution for all of our LRFD equations and the envelope solution for our ASD equations. And with that said, we can go ahead and run our first analysis with our result combination 1.
And you'll notice that this is nonlinear analysis. As I was saying, it's P delta. It solves rather quickly, and we are given the envelope solution for all of our LRFD equations. Maybe I want to jump to something more like load combination 3 here, 1.2 dead plus live plus wind. We can see our deflection is given at 0.779 for our slabs. We have deflections of our members. So what I was telling you is that in RFEM, you can see that all of these analysis options are available in RFEM alone. Our results tab popped up here. This allows us to maybe view our members, and I can turn this into wireframe mode. our member internal forces, such as our normal forces for our columns. Maybe we want to take a look at our shear forces. Moments, for example, we can always increase this diagram to make it a little bit more visible here, and you can print this off. So everything according to our analysis is complete. Support reactions is something else that I mentioned you can easily show. I just have some simple pin conditions and some pinned conditions at the bottom of our walls as line supports as well. So that's basically the extent of RFEM. So now for concrete design, this is where our add-on modules come into play. The first way to access these add-on modules, there's a tab up here called add-on modules. The options are a little bit more clear here in this list. Steel are grouped together, concrete are grouped together. So I could certainly access them through here. Back on our data or our project navigator and our data tab down here at the bottom, this is our long list of add-on modules. You can always right-click and add it to your favorite to move it up to the top of this list. I prefer to access it through here only because it's just a little bit quicker than going to this drop-down, but it's completely up to you. So the first thing that we want to do is to jump into our RF concrete members. So something to note here. This is our add-on module. And when I say add-on module, which avid RFEM users are used to this dialog box, but for others who are not familiar with our program, this is just a simple dialog box within RFEM. All of the materials, the cross sections, the loading, everything is taken from RFEM into this dialog box or our add-on module. So you don't have to worry about redefining any of that information. The add-on module is purely used for code design now. So you can see here that we have design according to ACI 318 2014 selected. Now the first thing the program asks us is what load combinations do we want to select for our strength limit state. We will probably use our LRFD equations for this scenario. That's pretty common. Now serviceability options, we will choose our ASD load combinations. That's typical as well for crack widths, and for deflections we want to choose our ASD load combinations. Down here, you'll notice under our serviceability, we have nonlinear calculations. This is if you want to take into account creep and shrinkage. I'm not going to get into this today, but this does require our additional add-on module, concrete nonlinear. So if you are wanting to take into account crack sections with creep and with shrinkage, this is certainly an option here. But like I said, I won't be getting into this today. We will just be sticking with the typical linear elastic analysis. Materials. As I mentioned, our 4000 F'(C) will be taken from RFEM. We have reinforcing steel grade 60. You can view the diagrams here for stress strain for both our concrete and our steel. All of the parameters are given here. Cross sections. We have the cross sections taken from RFEM. And let me exit out of this, turn this back into the rendered mode. And going back into the dialog box, I just wanted to show you that under our cross sections, it's nice because as we click on these different table rows here, the members that are applicable to this particular row will highlight in the RFEM model. So everything is synced together. We do have the option to optimize. If this is something that you want to consider to get the best design, the most economic design, all you need to do is just to check this checkbox. You can see that we have the option here to optimize. You can set target ranges for your width and your height, B and H. You can also set a target percentage of reinforcement. Sorry, I'm just double checking one other thing. Okay. Now, moving on down the list, we have our ribs cross section. This is the ribs category. You'll notice it highlights as I scroll through these different members back in the RFEM. This is the ribs that we defined at the beginning in RFEM that I was showing you. The effective width is taken into account, how we set it in RFEM. You can always override this directly in the add-on module as well. Supports. Supports is something important because in the code, when we're doing something like shear design, for example. The code says, well, you can take the required shear force a distance of d away from the face of the support. Now, in RFEM, and this is true for any finite element analysis program, members are just 1D member elements. They're modeled by their center lines. So we have no idea what the face of the support is. And what's great about this add-on module is that instead of maybe over-designing for a shear force that is much too high, we can specify these particular supports. All that I need to do is maybe I'll start with these nodes up here, and I just highlight. You'll notice these 4 nodes are now highlighted in red. I click OK. They're all available in this list here. Take note of this picture. As I change things without this table, this picture will automatically update. So support width. Our columns are a width of 20 inches. So I'm going to set my support width to 20 inches. For avid RFEM users, you may not be aware of this, but if you do press the F8 button, it will quickly fill in these cells according to what was previously entered. Direct support. This is self-explanatory just by looking at this picture. If I unselect this checkbox, this shows me that the beam is framing directly into that support. If I check it, it looks like it is a continuous beam resting on top of that support. For our case, we'll keep this as a direct support. Monolithic connection, is it 1 concrete pour or is it 2? Again, shown by this picture. End support. Is the beam continuous over the top of the support, or is this an end support condition? For our options up here, for our supports, they are an end support, and you'll notice the red arrow points to which node number I'm looking at. Again, this is great for large models. I don't have to guess, oh, okay, well, I don't remember what node 23 is, go back into RFEM, but everything is synced together. So now we jump into reinforcement. This is a little bit more lengthy than the other options that we've seen so far because we have a lot of code references and things to take into account according to the ACI for reinforcement design. The first thing the program asks us is maybe if we want to define more than 1 reinforcement group. This is important if you have a lot of members. Of course, they're not going to have the same reinforcement layout. So you can create as many groups as you'd like, and you can give them different description names. For us, we just have 1 description that we'll go ahead and define here. Applied to which member. So if you have many different reinforcement groups, you can apply them to different members. For the purpose of this demonstration today, I'm just going to select 1 member for design. Then we jump down here to our first tab, longitudinal reinforcement. What bars are possible for our reinforcement design? Well, let's say I want to choose maybe 5, 6, and 7 here. I'm not really sure exactly what will be needed, but we'll start with something like that. Max number of layers, this is pretty self-explanatory. If I want more than 1 layer, as you can see here, it's possible. Probably more important for larger beams when you're taking on larger loads. For our case, we will just have 1 layer. Something else that I would like to point out is the minimum spacing for the first layer. We have a user-defined entry here. So what we can do is refer back to the code, and this is chapter 25. The minimum spacing for our longitudinal reinforcement must be the greater of the values of 1 inch, the diameter of the bar, or 4/3 times the diameter of the aggregate. I have no idea what the diameter of the aggregate is. Probably as an engineer you might know that information, so of course you'd want to take that into consideration, but we do not in the program have an entry for that. 1 inch will probably be controlling here because I do have smaller bar sizes under a 1 inch diameter. Anchorage type. So anchorage and curtailment, I'll talk a little bit in more detail here. The anchorage type, we have every different option that you could probably consider. It's updated with this picture here. You'll notice we can take into account transverse bars. Maybe we just want a typical hook. For us, we'll just keep this as straight. Steel surface is grayed out because the code does call that all steel surfaces must be ribbed. Curtailment type. So curtailment is something that maybe we're not familiar with the term, others of us may be. So with that, I'm going to jump to my PowerPoint here and discuss what curtailment and a little bit more about our anchorage development lengths. Curtailment is where we can reduce the area of our flexural reinforcement along the length of our beam because we have a lower bending moment there. What this means is that this is going to save us materials and in turn save us money. It is an option in the program to take into account, and I'll show you just a minute how to do that. So the other option, or the other entry that we need to consider here that RFEM is doing in the background is the development length. The program knows whether the bars are in tension, compression, if they're a standard hook in tension, and it will refer to the code chapter 25 for all of these varying equations to make sure that these development lengths are correctly taken into account. Going back to our RFEM model, you can see curtailment type that we were just discussing. No curtailment means that we will simply be using the reinforcement throughout the entire length of the beam. So no curtailment means your top and bottom reinforcement will be taken the entire length of this beam number 14 that we're designing. Curtailment by zones. Here we can define the number of zones that we'd like to consider for curtailment. 3 is probably a good consideration. You might have higher negative moments towards the face of your column and higher positive moments towards the middle of the column. So by setting 3 zones, then we can optimize that reinforcement directly for those particular moments that are needed. Curtailment by reinforcement bars, this is just taking into account that the program will automatically create a new zone when the max number of bars is reached for that particular moment force that is required. And back in the PowerPoint, this is just taken directly from the code. It is figure 9732, and this is exactly what we're talking about. Probably towards the face of a column, we have more of a negative moment here. We have a very low moment in between here, so maybe we don't need as much reinforcement. This would be a situation where curtailment could be used, and then obviously we're getting into higher positive moments towards the middle span of the beam, which will require reinforcement on our bottom. Okay, for our case, we'll just leave it to no curtailment. Provided basic reinforcement. This is great for structures that are already existing. Maybe you already know the top and bottom area of steel. Well, here you can actually set that by just defining your number of bars, defining the bar diameter, and the program will automatically consider this as provided basic reinforcement. If this reinforcement does not meet the needs of what the design is calling for according to the ACI, the program will tell you, well, okay, we are considering this provided basic reinforcement, but we also need to add in additional bars in order to meet the requirements of our bending moments. Ties and stirrups. This is our next tab. Possible bars again. Maybe we want to consider number 3s and number 4s for our particular beam. The number of legs per section. This is updated with this little picture here. And keep in mind that the exact layout of our shear reinforcement doesn't really matter according to this picture. Basically, it's just telling you if you take a cut across this cross section for your shear reinforcement, the program needs to know, okay, well, I have the required reinforcement, but I need to know how to set this up according to my provided shear reinforcement, whether we have 2, 3, or 4 legs. Inclination. This is default to 90 degrees. Typically, we put our shear reinforcement at 90 degrees. You do have the option to change this, though. In the code, chapter 22, section 5, says that we have to use an inclination of 45 degrees or greater. So you don't want to put in anything, if you are following the code, less than 45 degrees here. It also tells us in the commentary that, of course, this is just common sense, that if you have shear cracks that are approximately the same angle as your shear reinforcement, well, your shear reinforcement is basically non-existent at that point. So that's just something to consider when you are putting in some type of angle other than 90 degrees here. Anchorage type, same scenario as our longitudinal, we give you different options for how you would like to anchor in these ties and stirrups. For us, we'll just keep it with the default as a hook. Stirrup layout and spacing, uniform spacing throughout. Do we just want, a single spacing consistent throughout the length of the beam? We can set zones here, just like what we did in curtailment, or we can go ahead and let the program automatically divide up these zones based on the different spacings. We'll keep uniform spacing for our example. Spacing limits. We do have the option to follow the code here, maximum link spacing according to the standard. So for stirrup layout and spacing, the max spacing is called out in Chapter 25, Section 7 as 16 times the diameter of the longitudinal bar, 48 times the diameter of the tie bar, or the smallest dimension of the member. So if you do leave this check, the program takes into account those provisions. As far as minimum spacings, this actually depends on the size of your aggregate. Again, there's no entry in RFEM or our add-on modules here for our aggregate size. So that's where you could possibly type in a minimum spacing here that you'd like. You can also define another maximum spacing, and the program will take whichever one is controlling. Reinforcement layout, concrete cover. This just comes from Chapter 20. It's Table 20.6131. We can consider our concrete cover here. Keep in mind that as I scroll through these, you'll notice that, again, this picture is synced up, so it's kind of nice that you know exactly what you're looking at. This is clear cover. This is the distance from the edge of the concrete to the edge of the reinforcement. Shear ties are considered in this as well. So this is why the cover to the centroidal axis is grayed out, because as I adjust this to maybe 2 inches, the cover to the centroidal axis will be adjusted as well based on what we put in there for possible bar size. Reinforcement layout. This is just how you want the layout for your top versus your bottom longitudinal reinforcement. Do we want it optimally distributed? Maybe we want a symmetrical distribution so that the top is the same as the bottom. We also have a couple options here to define the spacing or the layout based on ratios of our top steel area over our bottom steel area, over our total steel area. And we can also define it as maybe bundled bars in the corners here and uniformly surrounding, which is more typical for columns. For us, we will keep it as optimal distribution for our longitudinal reinforcement. Settings. These are the internal forces that the program is designing for. We get asked quite often, do we design according to torsion? Yes, we do. You can see here we take into account bending moment according to torsion. We also obviously design for our shear and moment as well as our axial forces. Minimum reinforcement. We have the 2 check boxes here to take into account minimum longitudinal reinforcement according to the ACI as well as the minimum shear reinforcement according to the ACI. If you have a user-defined minimum reinforcement, you just click on this little button. You can define the number of bars, the bar number, and the program will take that into account as well. Secondary reinforcement is for any reinforcement beyond what is required structurally. So if you are looking to put in a little bit more reinforcement than what are required is, this is where this will be done under the second reinforcement option here. ACI 318-14. Percentages of reinforcement. You can see the default is set at 8% here.
So this is something I'd like to go into a little bit more detail. We'll jump back to our PowerPoint here. And the code tells us that for flexural members and members where our axial load is less than 10% of the concrete strength times the gross area of the concrete, our net tensile strain must be greater than or equal to 0.004. This comes directly from the code, Chapter 9, Section 331. Now, compression members or columns, we actually are given a reinforcement percentage. So our steel area must be greater than 1% of the total area, but less than 8% of the total area. And this is explained further in Chapter 10, Section 611. A little bit of history about this. From 1963 to 2002, reinforcement ratios were used despite it being a compression member or a flexural member. We always use these ratios that you're used to down here for columns. Then in 2002, the ACI introduced strain limits, which is now what you're seeing according to Chapter 9331 up here. The purpose of this was to achieve uniformity with pre-stress, with reinforced, and with compression members. And I actually pulled all of this information from the journal called Case Studies in Structural Engineering. There's an article in there, Strain Limits versus Reinforcement Ratio Limits. So what's interesting about this article is that if you're an engineer and you're used to these reinforcement ratios pre-2002, and this net tensile strain just maybe isn't very intuitive to you, what this professor has done is actually to convert these stress equations back into ratios. And what he found was that there really was no difference. When we convert them back to ratios as a percentage of the gross area of concrete, it really comes close to the net tensile strain be greater than or equal to 0.004. So something worth checking out if you are interested in that. With that, we can jump back to our RFEM.
Back in RFEM, we do have this set at 8%, but keep in mind, according to the code for our flexural members, we need to check our tensile strain after our analysis because realistically, this is irrelevant if we are not meeting the code requirements for the tensile strain. Shear and torsion reinforcement, we have our nominal shear strength according to table 22.551 in the code. And then inclination of concrete strut, this is related to our torsion. The default is 45 degrees. You can certainly put in another angle, and for more information on this, it's probably best just to refer to the code chapter 22. Factors. Pretty self-explanatory here. If you've done concrete design, we're all familiar with our strength reduction factors. It is in chapter 21 of the code. These right now are set to what the code calls for. However, you certainly can change those if you choose to do so. But keep in mind, you probably, if you are doing design according to the ACI, then you will be following the code for these entries. Serviceability. This serviceability tab is only available because remember back in the Genera Data tab, we defined our ASD load combinations for serviceability. If I defined no load combinations here, if this was empty, I would not have this serviceability option here. So if that's missing, it's probably because you didn't define any serviceability load combinations. Crack analysis. So we have the options here to limit the value for allowable crack width based on a couple criteria. The first option is limit values, and you'll notice in this drop-down box, the ACI did some studies on various exposure conditions and came up with a limiting crack width that they think approximates what the max crack width should be. So for example, if you're in a water retaining structure, your crack width is much smaller than if you're in dry air. For us, maybe we'll stick to something like humidity. The structure is in, maybe down south where it's quite humid. Same for the bottom. So our crack allowable width is 0.012. Now you also have the option under user defined to just type in whatever you'd like. But we do need to give it some type of limit so that the program knows to flag it if we are over those limits. So how exactly do we determine what the crack width is? So what's interesting is in the ACI, the ACI does not give you an exact equation for how to calculate crack width. Basically in chapter 24, it tells you to limit the longitudinal spacing so that you can decrease your crack width, and that comes from exactly this, this section in the ACI. So when you have this checked, the program will limit your spacing based on this criteria. Now, if you're looking for more of a comparison to an actual crack width, well, then we need to turn to some equations that are more theoretical. Again, they're not found in the code. So in our program, we refer to the Gurglian-Lutz equation. And what this will do is this will calculate an actual width of your crack based on all of your loading and your criteria and such. So that's what this is about with our checkbox here. Deflection analysis, you'll notice when I check this box, I now have a new deflection data tab here. I can click on this. This is pretty self-explanatory. It's for our deflection limits. Because I'm only designing one member, member 14 here, I can set the reference length. Typically, maybe we'd choose the distance between the support, but you can also choose the member length, or you can maybe define your own user-defined reference length. For us, we will just stick to the distance between supports. You can put in here a pre-camber if you prefer, and then we have our limit values. Our limit values are things like L over 250, L over 200. You can put in here your own user-defined. So the program knows to flag if we have any deflection greater than the total length over 250, then we will fail in our serviceability checks. Back here under serviceability, we also have the option to activate long-term deflection according to 24241. This is just a table in the code that will take into account in the calculations for deflection the duration of the load, and we can set the number of months here. So with that said, I think that we are finally ready to run an analysis. Now, all I need to do is just click calculation in this add-on module, and what it's giving me now is reinforcement design according to ACI. So you'll see here that now all of this reinforcement or this results section is available here. The first thing to look at is our required reinforcement. In this table right here, we will see basically the summary of according to cross sections, or maybe we want to view it by member. Because we only defined one member here, we're still just looking at member number 14, so it doesn't matter. We're getting basically a summary of our reinforcement. So we have our reinforcement at the top given, our longitudinal reinforcement at the bottom, and then we have the reinforcement for required longitudinal torsion. And you'll notice this is set to 0. So this is only if it's applicable, if we have some torsion within this beam. Then we have our shear reinforcement. And lastly, we have our stirrup reinforcement for torsional moment. Again, this is 0 because we don't have much torsion in this particular beam. As I click through these different options, my stress strain diagram are updating here according to my cross section. And this is also something else that I really want to emphasize. There are a lot of other programs out there that you simply don't know where your numbers are coming from. And I really think that RFEM is such a strong and powerful program because we always try and give you as much information as possible. I know I've mentioned this before, but this allows for very few tech support calls to come in and emails saying, you know, I just don't understand where these numbers are coming from, because we list all variables here. We give code references where we can, so you can really understand where those numbers do come from. We can also view the required reinforcement by X location. What's nice again is that as I'm scrolling down through these different options, you'll notice this red arrow is updating depending on where I'm at along the length of the beam. So for large models, this is beneficial so that you can really understand what exactly you're looking at. And again, we have the long list here that updates as we scroll through these different options to show all of our variables and how we came up exactly with these numbers. So now that we know our required reinforcement, obviously the program needs to come out and give us some sort of design. And that's where this provided reinforcement comes into play. The first tab here is our longitudinal reinforcement. So in order to meet the required reinforcement, the program has set 3 number 7s up at the top here and 3 number 5s at the bottom to meet those requirements. What's nice here too is that if you take a look at this and you think, oh, you know, I'd really prefer not to use number 7 now. Well, I can easily check in this or click in this table here. I can maybe increase to 4 number bars, and I would like to use number 6s. I click OK. I can click on any one of these other tabs, and the program says, wait a second, you changed your values for your number of bars and the bar size. I need to recalculate. So you quickly recalculate, and the program will update only what's applicable to the changes you just made. So a very quick and efficient way, rather than jumping back into this reinforcement to force the bars the way that you would like them. What's also interesting here is we get this nice picture, but if I double click in it, I get the basically the 3D layout of my reinforcement. You can see here that I have my longitudinal reinforcement shown. I have my shear reinforcement. It even shows the development of my shear reinforcement as well. I'm given the callouts for the bar sizes as well as the number and the spacings. I have control here to turn on and off any of these reinforcement bars, and this is great for printing purposes. And just like in the tables, if I think, oh, shoot, never mind, I want to go back to 3 number 7s. Well, I can just double click in here and I'm given those exact same options that you just saw in the table. So again, this is a great and efficient way to quickly make changes. Maybe the anchorage type I decided needs to be a hook instead of straight. I click OK. Everything is automatically updated. So I click out of this picture, maybe I click on another tab, the program says, hey, you made changes, let's recalculate. I recalculate, it recalculates only those bars that had changes so that everything is updated in our results here. Shear reinforcement, same exact concept. We give you a nice cross-section here, including the lengths for the shear reinforcement and the development. Same thing, picture, we can double-click on it. It looks exactly like what we were just viewing. In both pictures, you can modify any of the reinforcement and add this to your printout report with just the click of a button. Reinforcement by X location. Basically just a summary here along the length of the beam. Again, this nice red arrow kind of shows us where we're at. We get a summary of our top and bottom longitudinal reinforcement as well as our shear reinforcement. And then, of course, as I always like to mention, here is our list of any variables and equations that went into calculating this reinforcement. Lastly, we have a steel schedule. This is your material takeoffs, which a lot of us, of course, are interested in the total steel. Serviceability check. This just relates back to the crack widths and the deflections. You can see that according to the deflections, we have a ratio of 0.41, so we are under those limitations that we did give it under the deflection data back here. Now we have our spacing limitations, which I mentioned the code calls out for cracking. And we also have the ratio according to the Gurgley-Lutz equation, which you can see here is calculated in comparison to the limiting crack widths that we also gave it in this criteria. So we can view it by cross-section or by member. Again, same scenario since we're only doing one design here, and of course by X location. Something else to notice in any of these tabs, you'll notice this notes section. If you see any numbers here and click on this messages, it should correlate to any, I don't know, warnings or just information that the program would like to give you about your reinforcement design. For example, this says 334, the effective bending moment MZ is not considered in the given deflections. So this is important if you are seeing those numbers to just quickly take a look at the messages. And the other thing that we can do is we can view everything graphically here. Maybe we want to take a look at our, so once I click graphics, you'll notice in my drop-down box here, I have another option called RF concrete members. Now in my results tab, I no longer have all of the internal forces from RFEM. I can easily jump back to those, but now I'm looking at the results from my concrete module. I can turn this back into wireframe. Maybe we want to take a look at our top and bottom reinforcement. This is nice. Maybe we want to add this to some pictures, and you have all of these options to view this graphically as well. Sometimes this makes a little bit more sense than viewing things over and over again in a table just to reiterate what exactly is going on. You can see here shear reinforcement, and actually you can even show that nice rendering picture that we were viewing in directly in the model. Again, maybe good for printing purposes just to show you how things are related here to the rest of the model. So with that said, that basically sums up our beam design. Now we want to jump into our column design. And before I do that, I want to go back to the PowerPoint because this is something that is very important in regards to column design. So we often get asked, okay, do you design columns according to the moment magnification procedure or second order analysis? And this is where I really want to clear up what's going on in our add-on modules. The code in ACI 2014 says that we have 4 different options to account for slenderness and curvature effects for our compression or our column members. The first is a first order analysis according to section 6.6. This is purely a linear first order analysis. Now, second order effects are taken into account with our moment magnification procedure. So those of you who've done column design probably are very familiar with the moment magnification procedure. Basically, this will just increase our moments, like I said, to account for those second order effects. What's great about the moment magnification procedure is that you as the engineer can easily cross-check these numbers in comparison to the software. So something when we're getting to a little bit more complicated analysis, it's not that easy to cross-check by hand calcs, but with this option, we certainly can do so. And first order analysis with moment magnification is taken into account in RF concrete columns. So this is the module that I will show you guys next. Again, to reiterate, first order analysis, RF concrete columns. Now, the second option the code gives us is elastic second order analysis. This is chapter 6, section 7. This is P delta effects. So this is done in the add-on module we were just in, RF concrete members. If you prefer to do a column analysis according to elastic second order with P delta effects, this is the add-on module you'll use. So realistically in our program, we have 2 different options to do column design. First order analysis with moment magnification, or to consider P delta effects with an elastic second order analysis in the add-on module we were just in, RF concrete members. For today, I'm going to stick with the first order analysis according to moment magnification. I mean, basically we just went through RF concrete members. Everything will be pretty self-explanatory when you go through there. The third option is an elastic second order analysis. Chapter 6, section 8. This is where material nonlinearity, member curvature, shrinkage, creep are all taken into account. What's interesting is in the ACI, it really doesn't give us much information on how to proceed with this. With that taken into account, our additional add-on module, RF concrete nonlinear, only takes into account shrinkage and creep for the ACI for serviceability. So at some point in the future, we do plan to add more options here for concrete nonlinear. Basically, this is taking into account the true cracked cross-sectional properties. So the program will calculate those correctly instead of just putting in that cracked multiplication factor that we do find in the code. So like I said, this is a little bit limited with ACI. It's more so geared towards the Eurocode now, but with that said, the ACI really doesn't give us much information. Now the last option, finite element analysis, is actually new in the 2014 code. This is in section 9. And again, not much information is provided. It just tells us that a computer software program can be used for our finite element analysis. So like I said, today we will just stick with the first order analysis according to our concrete columns.
Now, because we are working in this add-on module, RF concrete columns, it is according to linear analysis for our load combinations, and we take into account second order effects with the moment magnification as we just went over. So what I want to show you guys is how to exactly deal with this. So back in RFEM, this is in RFEM, not the add-on module, we want to go to our load combinations dialog box. As I previously showed you, all of these load combinations are according to second order analysis. What we actually want to do here is to select all of our load combinations and choose geometrically linear analysis. This is important so that we don't account for second order effects in RFEM, then we go into our RF concrete columns and we again account for second orders with moment magnification. Now the program is smart enough to throw up a little warning saying, hey, you are accounting for second order effects twice. Now realistically it's not that much of a difference if you choose to do so, but it will still warn you that you are accounting for them twice. So for the sake of this, to correctly take into account moment magnification, we want to change all of these load combinations to a linear analysis. Now, if you are jumping back and forth between beam and column design, maybe you want to make a copy of these load combinations, set half of them to linear analysis and set the second half to second order analysis. Then you can individually assign those load combinations in these separate add-on modules. So now that that is done, we can go into our concrete columns and take a look at our design loads here. So now all of these design loads are ready to go with a linear analysis taken into consideration.
So here, this module looks very similar to what we were just in, but you'll notice we're in the concrete columns add-on module here. We need to define the members or the sets of members. If I go back to the add-on module and I turn this into wireframe, you'll notice these two columns here, and it has this dotted line around it. This dotted line means that it's a set of members, and the reason why I did that is because we probably want to design these two columns to have the same reinforcement, maybe the same size, maybe they'll be cast as one continuous member, whatever it is. We probably want the same design for all of them. So all I need to do is just to right-click, select both of them, right-click, and then here I can create a set of members. This is a continuous member now. So when we're back in this add-on module, instead of designing each individual member, I have the option down here to design according to my member set. So I'm going to design according to this single member set here for the purpose of this example. Strength limit state. I am going to choose my LRFD equations here. And then we get into our sustain and sway loads. And this gets a little bit confusing because this is obviously very different than just our typical strength and our ASD load combinations for serviceability. So going back to the PowerPoint, I do expand on this a little bit further. Here, as I mentioned, we are doing a first order analysis. I know I repeat that a lot, but that is the whole purpose of this add-on module. And as you notice, we have the strength limit state, sustain loads, sway loads. As I just mentioned, strength limit state load combinations will be used for design are typically LRFD. Now, sustain loads, this comes from section 66311 and this other section here. And this just tells us that we need to take into account additional deflections due to creep. This doesn't necessarily have to be a gravity load, but this could be a lateral load as well. Typically, you'll find things like dead load, though, are something you want to consider for creep. And that's where we would add this into the sustained load, something like our load case dead load. And here we'll divide our stiffness by, our stiffness EI by 1 plus the sustained load factor. In turn, this increases our second order moments done in the moment magnification procedure. So, like I said, if creep is something you want to consider, you will want to add that into the sustained loads tab. Sway loads. This is in Chapter 6, Section 646. This is if we have any lateral loads causing lateral deflections that we want to consider. This is wind loads, earthquake loads, loads of those various types. And here the reason why we have to do that is because there's a much different approach for sway versus non-sway in the moment magnification factor. So by putting loads in the sway loads, everything else will be considered non-sway. So jumping back into the RFEM model, as I mentioned, we put our LRFD equations for strength. Sustained loads are anything we want to consider for creep. So I'll add my load case dead load here. And lastly, we have sway loads. As I mentioned, probably something like wind, earthquake, and such. If you have more than one sway load, you can always create a load combination here of wind plus earthquake. And the reason why, and this is very important to remember, is that back on the strength limit state, we now have this drop down available, and we need to choose which loads in this load combination are used for sway purposes. So here you can see I'm selecting the load case 3 for wind. This is what I put under my sway loads. It's now available in this drop down. So that's just a little bit about why we have these different tabs. They really do affect the moment magnification procedure. Materials. Again, a lot of this is just going to be repeat information from the previous add-on module, so I'm not going to spend a significant amount of time. Materials is taken from RFEM. We have our cross sections. You'll notice we don't have the option here to optimize, so just something to keep in mind within this concrete columns. And then reinforcement, again, we just choose the reinforcement type that we would like to consider. The layout is typically uniformly surrounding for columns. Anchorage type, again, we have straight hook bend. We also have the option to consider steel surface such as zinc coated or epoxy coated. This will be added in our other add-on module fairly soon as well because it does affect your development length. Ties and stirrups, same concept as before. We'll select number 3 as and number 4 to be considered. Secondary reinforcement, again, this is just any reinforcement beyond what is structurally needed. For us, we won't consider this. Reinforcement layout, you have the option here to define your cover according to the centroidal axis or the edge of the rebar. I always like to choose the edge of the rebar. It just makes a little bit more sense to me. And then the centroidal axis will be updated considering your shear reinforcement as well as the half the distance, the diameter of the longitudinal reinforcement. The program also asks us the bar number to be considered for preliminary design. Well, maybe I want to choose the most economical, number 4, for example. Relevant internal forces for concrete design. You'll notice here we do not design for torsion within this add-on module. So if torsion is something you want to consider for your columns, you would need to do so in the concrete members with P-delta effects and that sort of application. In the code under the column sections in ACI, it really just says, hey, if you have torsion that exceeds a certain amount, refer back to the beams. So that's why we really don't have an option here to design for torsion, but it is possible in RFEM itself. And lastly, ACI 31814, this is all the exact same stuff that we just saw previously, giving our longitudinal reinforcement minimums and maximums, our strength reduction factors according to the code, as well as our shear reinforcement. Notice that torsional reinforcement is not considered here. Parameters is something that is lastly important for the moment magnification procedure as well. Here, if we want to consider buckling about our Y or Z axis, which is given here, and by the way, you can always, maybe you are not sure about your Y or Z axis, you can always right-click on your members and turn the local axis system on. So now we can see what direction is Z and X. We can even turn this into a rendered view so that we can view, if we didn't have a square column, what exactly is going on with our local axes. So with our parameters here, we want to define if buckling's or if buckling is possible. Is it unbraced or is it braced? And the program will automatically calculate these K factors according to the code. You know, we have those different charts in the ACI that will calculate these K factors, and the program takes all of those into account. Same thing with buckling about the Z-axis. For this option, I'll just leave this unchecked for now just for simplicity. Again, all of our information is given here in the tables down below. So now we're simply ready to run a calculation. Should be basically what you're used to seeing in the other add-on module, but now we have a set of members that we're designing for. The first thing that pops up with our results is our check, our set of members. So you'll see here that we have our design ratio, and we have the code reference immediately available here. This is really nice, so you know exactly what's controlling overall for this particular column design. And Right now we have a check of critical cross-section of the model according to 6.2. Our shear check is according to 22,561. We have our nice green smiley face because we are below 1. And as I always love to point out again, everything is available here in our table, all variables that came into play with any of these checks and code references where they're applicable. So again, not a black box type program, but anything that you'd like to know how this came into account for the calculations, we try as best we can to put it into the program. You also have these little pictures down here. We can view the stress diagram of the concrete. We can give it value. So if this is something you're kind of interested in, this is available here. Required reinforcement, this should look a little bit similar to our other add-on module. Obviously here we're only giving longitudinal and shear. We don't do torsion. We're just given the basic layout for those. And lastly, the provided reinforcement. This looks just like our picture for beams. We can double click. We're given a nice 3D rendering. Just like with the beams as well, we can double click on any of this reinforcement to quickly change it if we'd like to force it to be another size, another spacing, whatever else you please. And we can view everything graphically. As I mentioned with the other add-on module, same procedure here. So you can see there's really not a whole lot of differences between the members and columns add-on module. So it's nice. Once you get the hang of maybe beam design, you can also easily do your column design as well. But like I said, to emphasize, again, it all just depends on how you want to do your column design. Is it according to moment magnification? Well, then you would want to use the concrete columns. If you'd like to do it according to concrete members, then you would choose P delta. So with that, that basically sums up the reinforcement design according to ACI for our beams and our columns. I do apologize about the issues with the load combinations, and like I mentioned, I'll be sure to correct that for the recording on our YouTube so that you can refer to the recorded webinar and use that as a reference point if you are trying to model yourself. So for more information, feel free to visit our website at dlubal.com. We have plenty of other recorded webinars on our YouTube site. You can find that on our website as well, Facebook, LinkedIn, and such. We also have our email address to the U.S. office, info-us@dlubal.com. So if you'd like to get in touch with me or the U.S. office, this is the email that you'd like to use. The phone number is 267-702-2815. We will certainly have more upcoming webinars. As I mentioned, the next webinar we plan to do next month is concrete slab and wall design or surface design according to the ACI. You can register for that on our website under Support and Learning and Webinars. As always, I try and send out a couple of emails just to remind you that's coming up. For those of you that are interested in PDH credit, please email me at info-us@dlubal.com. and I will be happy to issue that certificate to you. With that said, that concludes today's webinar. So I want to thank everyone for attending today, and I hope to see you at the next webinar.